Kepler's law. So Kepler's law, so like I was saying just now, Kepler's laws are the laws that were discovered or theorized by the scientist Kepler. You learned about him in Form 3. So this is a German astronomist, mathematician, and astrologist who modified the heliocentric model according to Kepler's laws. So these are the three laws. And these three laws are what affects our modern understanding of how the planets move around the sun. Okay, so that's what Kepler's laws are talking about. It talks about how the three planets behave as they go around the sun, right? And it helps us. This is also what helps people predict and calculate how far the planets are away from each other and how long it takes for the planets to go around the sun and things like that. So there are only three laws, but each of the three laws are actually quite interesting, and they explain a lot about how the planets move around. So let's start with the first one. Kepler's first law, also known as law of orbits. All planets move in elliptical orbits with the sun at one focus. Okay, so every single planet that we've been able to study so far, meaning to say the planets in our solar system, move in elliptical orbits. So what is elliptical? So elliptical, when I say elliptical, so the shape of an elliptical is, we have perfect circles. Okay, obviously I can't draw a perfect circle, but imagine that this is a perfect circle. So we have perfect circles. Now, the orbit of a planet is not a perfect circle. Rather, instead of being a perfect circle, it is an elliptical shape. So it's more like in the shape of an oval or in the shape of an egg. So the planets actually, when they go around the sun, they actually do not go around in a perfect circle, but rather it goes in an elliptical orbit. Now, is that important or not? Actually, yes, it does affect some things. You will see later how the first law is related to the second and third law after this. All right. So the planets in the solar system have elliptical shaped orbits. Okay. Figure 3.25, which we'll see later, or you can also see in your textbooks, shows the sun always stays on a focus of the ellipse, meaning to say, even though it's always going around, the sun will be a focus. It's going around the sun, but the sun is not always exactly in the middle, and we'll see that later. The axis, meaning to say if we were to take a line and go from one point to the other point of the circle, of the ellipse, the major axis is longer than the minor axis. Okay. Now, most planets in the solar system have major axis and minor axis of almost the same length. Not exactly, but almost. Meaning to say, the shape of the elliptical orbit is almost round. So it's not a perfect circle, but it's almost a circle. Right? So when we're making calculations, when we are doing mathematical calculations, even though we know the movement of the planet is not a perfect circle, but when we're doing the calculations, we will just assume it's making a perfect circular motion. All right? So that's an important thing. When we are doing the calculations, when we write it down, our formulas and whatever, we assume, kita anggap saja yang putaran planet mengelilingi matahari adalah bulatan yang sempurna. But in actual reality, it's not a perfect circle, but rather it is in the shape of an ellipse or elliptical. The radius of the orbit is the average value between the distance between the planet and the sun. So, bila kamu kira radius orbit, apa yang mereka lakukan ialah mereka ambil radius yang paling jauh. So sometimes the planet is a little bit further away, and mereka akan ambil radius yang paling pendek when it's closest to the sun, and then they'll find the average. Mereka akan kira purata and they'll just use that as the radius of the circle around the sun. Okay. So here's the picture. So as you see here, the sun is actually not in the exact middle of the orbit. Sometimes the planet will actually be further away from the sun, and sometimes the planet will actually be a little bit closer to the sun. So that's why it's very interesting how it works. There are times when it's closer and there are times where it's nearer. Now, you can also see that there are lines that we use to divide the orbit. So you can divide the orbit in two ways. We have the major axis. So the major axis is longer, the long one. If you divide it in half, it's longer. We also have the minor axis, where the minor axis is actually a little bit shorter. So meaning to say one is a little bit longer than the other, meaning the shape is not a perfect circle, but it will be a, like we said, an ellipse or an egg shape, an oval shape. Now, if the minor and major axes were both exactly the same length, then actually it would be a perfect circle. But in most cases, not in most cases, in all cases, it is not a perfect circle. But like what we said earlier, even though it's not exactly the same, it's almost the same. It's close enough that when we are making our mathematical, when we are doing the maths, we'll just assume that it's a perfect circle. Okay, so keep that in mind. Remember, in reality, it's not a perfect circle, but when we're calculating, it's close enough that we can just use a perfect circle. All right. So I hope that's clear for now. If you have any questions, just go ahead and continue to ask anytime in the chat. So that's the first law. The law is that planets go around the sun in the shape of an ellipse and not a perfect circle. Second law. All right. So this also has to do with the first one. A line that connects to a planet to the sun, sweeps out equal areas in equal times. So first of all, here's a good picture. So observe figure 3.26. If a planet takes the same amount of time to move from A to B. So here on the left side of the picture, there's a planet. A planet moves from point A to point B. And then on the other side, when it's far away from the sun, when it moves from C to D. All right. If these two travel distances from A to B and also C to D, if it takes the same amount of time, maksudnya, let's say from A to B is 2 weeks, and from C to D is also 2 weeks. If we were to connect the lines, let's make a line from A to the sun and from B to the sun and take out a section here. The area of that part will be the same as the area of the second part. So ABF is the same area as CDF. All right? If we use the same amount of time. Meaning to say, when the planet is closer to the sun, it actually moves faster because it has to cover the same area in the same amount of time, but it needs to move further away. It needs to spend more time. It needs to make a further radius than compared to when it's further away from the sun. So when a planet is further away from the sun, it actually is moving a little bit slower. Okay, maybe not a great difference, but it's still a little bit slower. So the two things that we need to know about Kepler's second law is, first, okay, kalau kita ambil dia punya area in the same amount of time, A to B and C to D, tidak kira lah mana-mana saja di dalam ini orbit dia. Kalau dia mengambil masa yang sama, then area yang dia akan cover ataupun dia akan sweep adalah sama. And second of all, when you talk about the speed of the planet, semakin dekat sebuah planet kepada matahari, dia sebenarnya akan bergerak dengan lebih cepat berbanding bila dia lebih jauh daripada planet. So if we were to write this out, if t time is the same, then ABF, so area of ABF will equal area of CDF. If the time taken for the orbit of both parts or both sections is the same. Right? Yes. So that would be Kepler's second law. Right. Okay. So far, do you have any questions for the first and second law? Right. The first and second law isn't that long, but they do help us understand some of the things about planets and especially a little bit also about the third law. The third law is where we'll be spending most of our time today. Okay, no questions yet, so I will just continue. So Kepler's third law. Okay, this is where it starts to get a little bit longer. That's why we'll spend a lot of time. So wait, before I go that, the first law is also known as the law of orbits. The second law is known as the law of areas because it talks about the areas. The third law is also known as the law of periods, also known as the law of harmonies. So either one of those two names, it's talking about the same thing. So Kepler's third law states something like this. The square of the orbital period of any planet is directly proportional to the cube of the radius of its orbit. Alright? Orbital period meaning how long does it take for the planet to go around the sun? So for example, our planet Earth, how long does it take for the planet Earth to go around the sun? It takes, well, we know it's about 365 plus 1 over 4 days. So somewhere around there. So 365.25 days to go around the sun one time. And on the other hand, we also have t. So t is radius of the orbit, distance from the planet to the sun. So there is a direct relationship between these two. So semakin besar, I mean it makes sense, right? Semakin besar, also I should say the radius. Semakin besar itu radius, itu orbit, meaning to say the further away the planet is from the sun. And of course, it makes sense that it will take longer for this planet to go around the sun because it has more distance to go around. But it's actually an exact relationship. It's directly proportional, which is the cube of the radius is directly proportional to the square of the time or the orbital period. It's yeah. So this is the one that we have some calculations to do. Some of you might be a little bit confused, but don't worry, we will go as we go on. Hopefully, it will help you understand a little bit better. So a planet which orbits with a larger radius has a longer orbital period. Of course, that makes sense. Larger radius meaning to say it's further away from the sun. So since it's further away from the sun, it takes a longer time for it to go around the sun. Okay, so for example, the Earth takes 1 year to make a complete orbit around the sun, while Saturn, the planet Saturn, which is further away from the sun, takes about 20, almost 30 years just to go around the sun one time. So this is also in your textbook. It's not very clear, but if you have your textbooks, you can look at it. So just to give you a comparison, the Earth takes about 1 year. The Earth takes 1 year to go around the sun. Okay, the planets that are closer to the sun takes less time. The planets like Mercury only takes 0.2 years. So 0.2, so 12 times 0.2 is what? Around what? Around 3 months? No, not even 3 months. Like 1.5 months, 6 weeks, about 6 weeks to go around the sun. So Mercury, let's say, takes about 2 months to go around the sun. So in 1 year, so 1 year on Earth, Bumi baru pusing matahari satu kali, Mercury dia sudah pusing about 5 times. Okay, the next planet, Venus, it takes about 0.6 years to go around the sun. So Earth takes 1 year to go around the sun. The next planet, Mars, takes 1.9 years, so almost 2 years to go around the sun. So summer on Mars is 6 months instead of 3 months, for example. All right. Then next, what we have, the next planet is Jupiter. Jupiter is much further away. It takes almost 12 years to go around the sun. And then Saturn takes almost 30 years to go around the sun. And then next, Uranus is 84 years. And then Neptune, which is the furthest planet, official planet, takes 164 years to go around the sun. So the further away from the sun, the longer it takes for it to go around the sun. And we can calculate it using this relationship. That should be a small letter r. That's a mistake. That's not a capital letter R, but a small letter r. So t square is, I wrote that completely wrong. I'm sorry. T square is directly proportional to r cube. It shouldn't be square, r cube. Yeah, here's the correct formula. So, meaning to say, yeah, we've talked about that already. Okay, so Kepler's law. So how did they come up with this? How did Kepler figure this out, or how did they manage to calculate this? So Kepler's third law can be formulated using Newton's universal law of gravitation and concept of circular motion. So we can use these two formulas, which we have learned in our last chapter, to come up with Kepler's third law. Alright, so we can make the formula for Kepler's third law. So planet makes circular motions around the sun, and we already learned that the centripetal force equals the gravitational force between the planet and the sun. Itu kita sudah belajar di 3.1, right? So since we know that assuming that the orbit of the planet is circular, all right, we can derive the relationship between the orbital period of the planet and the radius of the orbit, as in Kepler's third law. So let's say we have this information. So we have the mass of the sun, we have the mass of the planet. Remember, we use the mass to determine the gravitational pull. We have the radius, we have the distance. We also have the velocity, because the velocity, remember, we need the velocity when we're calculating centripetal force. Okay? These are both formulas that we already learned last time. All right, so these are the two formulas that we have learned before. Gravitational force, F equals gmm r square, right? And centripetal force we learned is mv square over r. So, okay, I'm going to show you this. This is how it's shown in the textbooks. But I'm also going to show how it's done one by one lah. All right. So if I were to write this out one by one, this is what it would look like. So sorry, give me a moment. So let's look at the two formulas that we learned before. Gravitational force, F equals G M. Big M is the mass of the bigger planet or the sun. Small letter m is the mass of the planet. R square, R being the radius from each other. All right. Now the second one, this is gravitation. Okay. Next is centripetal force, equals mv. Now, because these two are the same, is going to be the same, we can substitute F with the formula. So we can say, therefore, G capital M R square equals mv over r, right? Since they are both equal to each other. Okay. Now, if we were to rearrange it, we would end up with, we would basically end up with this. So we can cancel this one out, right? And we can cancel this one out. And so what do we have left? So what we have left is, if we were to make this V as this on one side, we could actually rearrange it and end up with this formula. So V squared equals Gm over R. Alright, so this is the first step basically. The second step is to figure out what is the linear speed of the planet. How do we do that? Alright, so how do we figure out the speed of the planet? Well, we can figure out the speed of the planet by calculating what is the distance, what is the, we can calculate it by figuring out how long is the perimeter of the circle. And we know that the formula of perimeter of circle is 2πr. And we can divide it by the orbital period, or the time it takes for it to go around the sun. Right? So, yeah, linear speed of planet V equals distance traveled in one complete orbit divided by the orbital period. So, let's write that down. So, how do we know the distance, okay, or speed of the planet? So, linear speed of planet, all right, equals V equals distance traveled, right, over time. That's velocity. We know that already. This is just a formula for velocity. So, in a circle, what's the distance traveled? Since it's a circle, we will use the formula for circle. So 2πr. Time, we don't know, but we'll use t. T for the orbital period. So now we have these two formulas to use, for us to use in this equation. So we will use this as number 2. And then now what's the next step? So if we look at the next step now, the next step is to do a substitution. Alright, so next step is we do a substitution. So let me write out what we have so far. So what we have so far is that this. So far what we've calculated is V square equals G gravitational constant mass over R. That's the first one that we calculated. The second one that we calculated is that V equals 2p or pi of R over T. Alright, so now this is 1, this is 2. We can do substitution. We can substitute this V for this V. So, we substitute, so 2p r t square equals gm r. Okay, and so after you calculate everything and simplify everything, I'm not going to do the whole thing, you end up with this formula. So after you finish simplifying it, you end up with t square equals 4p square over gm r cube. Now, this is where we get the relationship. T square r cube. This is constant. Alright, the value of g does not change. The value of the sun is not going to change. The value of pi is also not going to change. Right? You don't change the value of pi. Pi is always going to be 3.14. So the only thing that's going to change is this one and this one. And if this one increases, then this one will increase. So that's how they came up with this. So that's it. That is the full mathematical formula. That is the relationship between the square of the time orbital period and the radius, the cube of the radius of the orbit. Okay. So far I'm only talking about how they came up with the formulas in your questions and in your textbooks. Um, if I were, this is the simplified version of everything that I just talked about. So when we combined these two formulas, centripetal force and gravitational force, with the formula for the velocity of the planet, you end up with this formula where there is a relationship between the uh, orbital period, time it takes for it to go around the sun, and the radius, cube of the radius. Right? Now, all of that is interesting and good, but how do we use it? How do we solve problems? Okay. So we have, um, so now we have a couple of things that we need to first. Oh, sorry, no. First, take a look at this. This is also in your textbook. I didn't have time to type it out, so I just screenshotted your textbooks and put it up there. From Kepler's third law, we just talked about this. So Kepler's law is the relationship is t square equals parenthesis 4 pi square over gm parenthesis r cube. So when we compare two planets, we can actually use this formula to compare two planets. So t1 square over t square 1 over t square 2 equals r cube 1 over r cube 2. So these are the two formulas that you're going to use the most in the calculations. So this one. So the two formulas that you need to remember is this one that we just talked about. 4 pi square over g m r cube. You need to remember this formula. And you also need to remember this one. T21 over T22 equals R31 over R32. This is what we use when comparing two planets. For comparing planets. Okay? Let's go into two examples from your textbook. All right. So here is the first picture. If you have the textbooks, you can follow along. So here you can see that there are two planets that we are going to compare. So we have the Earth and we have the planet Mars. This is on page 100. Page 100 and page 101 and page 102. All right. So as you can see, the Earth has its own radius R1 away from the sun, and Mars has its own radius of its orbit, which is R2. And the orbital period is also T1 and T2. So let's see the first question. First question is, the radius of the orbit of the planet of Mars can be determined by comparing the orbit of Mars with the orbit of the Earth. So the question is, what information is needed to determine the radius of the orbit of Mars? So this is an interesting question. So the question is, what information is needed to determine the radius of the orbit of Mars? So for us to answer this question, first we have to figure out what formula are we using, right? So we have to ask, what formula can we use to compare two planets? Now we just talked about this just now. To compare two planets, we need to use this formula, t square 1, t square 2 over r cube 1 of r cube 2. Right? So this is the formula that's what we're going to use. So let's write that down. So the formula that we are going to use is T1, T2, 2, r cube 1, r cube 2, right? So that's the formula that we're going to use. Now, we've seen, if we go back to looking at the question, we already have that. We already have R1 and R2. So we already know. We have to so now let's write down which one is which. Alright, so orbital, sorry. So T1 is orbital period of Earth. This is just based on what's in the graph or in the picture. Let me just move that a bit so that. All right, and then what else is in the picture? We have the orbital period of Mars, so T2. Of Mars is T2. Okay, R1 is the distance, the radius of Earth's orbit, and R2 is radius of Mars orbit. Okay, so let's go back to the question. The question is, what information is needed to determine the radius of the orbit of Mars? So radius of the orbit of Mars is R2. So in order to be able to find R2, we need to know T1, T2, and R1. So the information that you need, so when you answer this kind of question, then the way you're going to answer it, you have to answer this in the form of a sentence lah. Alright? So the way your textbooks answer this, it writes out down this sentence. I'm just going to read it out for you. The orbit of the planet Mars can be determined by comparing the orbit of Mars with the orbit of the Earth. Yes, so the solution is, what information do you need? You need to know the radius of the orbit of the Earth, the orbital period of the Earth, and the orbital period of Mars. So whatever information you're looking for, it's the other three that you need to find the information. So that's how you answer the question. I'm just doing it the long way so that you can show it. Actually, you can just tell by looking at the question. So that is just the first question. All right, second question. Now the second question is, we're going to do some calculations. So the question is, the radius of the Earth is 1.5 times 1,100 m. Hey, is that correct? I think that's incorrect. Sorry. There we go. All right, there you go. So no wonder that's wrong. So sorry, I wrote that wrong. But radius of the Earth is 1.5 times 10 power of 11 meters. The orbital period of Earth and Mars is 1 year and 1.88 years respectively. Calculate the radius of the orbit of Mars. So let's look at that question. Let's write it down one by one so that we can understand. So radius of the Earth. So R1, what is the value of R1? So R1 is already stated to be 1.5 times 10 power of 11 meters. So we already have R1. Okay. Orbital period. So R2, not given. That is what we are looking for. Okay. Now orbital period of the Earth, T1. All right, is 1 year. And for Mars, T2, it's stated to be 1.88 years. All right. So now we have all the information we need to calculate everything. All right, so now that we have the all the information, we just need to choose the formula. So we've already chosen our formula ahead of time because the formula that we're going to use is this one. So t1 square over t2 square equals r1 cube over r2 cube. All right. So now we just need to put it in our solution. So if we were to write it out, so it's going to look something like this. So 1 okay, so there you go. So 1.5 10 power of 11 cube, remember it's cube, over r2 cube. R2 because we don't know how much is it, equals 1 square over 1.88 square. Right? And if we do the whole calculation, so if we do the whole calculation, we'd end up with r. Well, first we need to rearrange everything. So r2 square equals, r2 cube equals 1.5 times 10 power of 11 cube times 1.88 square over 1 square. And we also need to remove the cube, so we move the cube to the other side. We find the cube root, and put everything in its place. All right. Now, if you're using a calculator or if you're calculating this at home, you may choose to do it step by step instead. And so your final answer comes out to R2 equals 2.28 times 10 power of 11 meters. So further away, so the radius of Mars is further away because because of that it also takes a longer time for it to go around the sun. All right, so that is how we use that formula. That is how we use that's how we use the Kepler's law to study about the different planets, plus also using the law of gravitation and also using centripetal force. Okay, let's try one more example. All right, one more example. This time we're comparing a planet. This time we're comparing the moon and a satellite. So this time instead of the sun, we're using the Earth as the center using it as the focus. But the idea is still the same. So figure 3.31 shows that a research satellite needs to orbit at a height of 380 kilometers to capture clear images of the surface of the Earth. What is the orbital period of the satellite? Okay, the orbital period of the satellite, and where was I? And the radius of the orbit of the moon is also given, and the orbital period of the moon is also given. So once again, we use the same steps as always. First, we need to see what information we have. So, all right. First, we need to clear out the whiteboard. Okay, let's see. Let's see what information we already have. So I'm going to go back to the question. Okay, so the first information that is given is radius of the orbit of the moon. So R1 and R2 is given. Oh no, R1 is not given. I'm sorry. So R2 is stated to be 3.83 times 10 power of 8 meters. So write that down. Everything is always going to be written down. Let me just adjust that so that we can see everything better. Let me just adjust that a bit. Alright. So first we'll write that down. R2. Next, R1. What is R1? Radius of the satellite. Orbital period of the satellite is not mentioned. Alright, so R1 not yet mentioned in the question. Okay. It's mentioned to be at a height of 380 kilometers. Sorry. So we need to change that into meters. So we need to go times 1000. And so we should end up with 380,000 meters, right? But we can convert it to standard form. So 1, 2, 3, 4, 5. So we can write it as by the power of 5, right? So that we can both have similar answers. So we have R1, R2. Now, the next thing is, what is the orbital period of the satellite? So, first of all, what is the orbital period of the moon? Orbital period of the moon, T1 is given to be T2. 655.2 hours. So it takes the moon about 655.2 hours to go around the Earth one time. And finally, T1 is not stated anywhere in the question, and that is what we need to find. Orbital period of the satellite. How long or how much time does it take for the satellite to go around the moon? All right, now that we have that, we can put everything in the formula. So we'll just put it in the formula. Where was I? Sorry, I made a mistake there. Sorry. For the radius, you have to add. Saya lupa pula tulis. For the radius of the satellite, you also need to add the distance from the surface of the planet to the center of the planet. Because tadi if you look at the question, it only mentions the height. The height of the satellite is 380 kilometers. Correct? That's correct. But remember that when we are talking about gravity, you do not only measure until the surface of the Earth, but you need to measure all the way until the center. So we also need to add the distance of the surface of the Earth to the surface of the Earth to the center. So we have to add 6.575 times 10 power of 6. So if we were to finish up everything, we end up with your final answer. With your final radius of the orbit of the satellite is 6.75 times 10 power of 6. Alright, now that we have all the information, just put everything in the formula. So what is the formula? Again, we know T cube 1 over T square 2 equals R1 cube over R2 cube. Alright, now let's do it slowly. We'll do it step by step. And then we're gonna go T21 is unknown. 655.2 square. 6.75 10 power of 6 cube. Yeah, I'm running out of space. 3.82 times 10 power of 8 cube. Okay, I'm running out of space, so I'm not gonna write out the whole thing. But if you write out the whole thing, you end up with T1. We move this to the other side and we find the cube root you get is 1.53 hours. Okay. Check your textbooks for the full solution. It'll give you the full solution for everything. Okay. So that's it for all the examples that we have in our textbook. Now I know it's not the easiest topic. So do you have any questions? Would you like to ask anything before I let you do before I ask you to do formative practice 3.2? Anything that you're still not completely clear or sure about?